Hey Math HL. So in this video, we're going to take a look at what's called the vector product. So remember earlier in this unit, we looked at something called the scalar product, which we also call the dot product. Now we're going to look at the vector product, which is also called the cross product. More frequently, it is called the cross product. So that means there are actually two different ways to multiply vectors. There's the dot product way of multiplying vectors, and then the way that we're going to see now. Each of them is useful for different applications, and that's part of what we'll get into after we go about learning how exactly do we find a vector product. So we're going to look at how to do that and then look at some applications of it as well. So let's say we have vector v represented by v1, v2, v3, and we have vector w represented by w1, w2, w3. And we want to come up with the cross product for v and w. By the way, cross product only works in 3 dimensions. It does not work in 2 dimensions. It also doesn't work in higher dimensions. It only works in 3 dimensions. Whereas scalar product, the other one that we learned, scalar product or dot product, works in any dimension. But cross product only works in 3. So here's how we compute a cross product. So the cross product of 2 vectors results in another vector. So when we multiply 2 vectors together in this way, the answer we get is a vector. So how we do that is, for the x component of the vector, here's what we do. We ignore row number 1 if we think of v1 and w1 as being row number 1. And then we multiply v2 times w3. I typoed. We multiply v2 times w3 minus w2 times v3. So you kind of make this sort of like shape like this, like a fish almost. So v2 w3 minus w2 v3. Now to get the y component, you do the same thing, but you cover up the y's. So you cover up v2 and w2. And this time, actually, you're going to do the fish thing, but backwards. So if you consider the v2 and w2 covered up, we're going to start at w1. So w1 v3 minus v1 w3. And that's how you get the y component of your cross product. And then your z component goes back to how we did this. We did for x. So you're going to cover up the z component, and then you're going to make that sort of fish shape in the same direction you did for x. So you're going to start up at v1, v1 w2 minus w1 v2, v1 w2 minus w1 v2. And that's how you find the cross product. So a cross product or vector product will result in a new vector. Let's actually work that out for a problem. So I usually like to write my vectors out vertically when I'm doing this. And I wrote it with kind of a lot of space so that I can cover things up easily. So to figure out the x component of the dot product or the vector product of these, I'm going to take and cover up the x part. I'm going to do -2 times -4 minus 3 times 3. Okay, now for the y, I cover up the y components, and I do the little fish thing backwards. I start at the top right instead of the top left. So I'll do 2 times 3. So 2 times 3 minus 1 times -4. For my z component, I go back to starting on the upper left this time. So I cover up the z's, start at the upper left, 1 times 3 minus 2 times -2. Okay, so let's see what vector that results in. So I get 8 minus 9, so -1. I get 6 plus 4, so 10. And I get 3 plus 4, so 7. So that is, if we want to write it back in the original form they gave me, we wouldn't have to do that necessarily, but if you wanted to write it back in that original form, I'd have the vector -I plus 10j plus 7k. So that is the vector product of those two vectors. Okay, so just like we can do stuff with the scalar product, we had a formula that included. We can do stuff with the cross product as well. And the formula that we are going to put together is that if we take the magnitude of vector w, if we take vector v, cross it with vector w, and we want the magnitude of that. So we want to know how long the resulting magnitude is of this guy. The formula for that is that we can take the magnitude of v, multiply that times the magnitude of w, and then do the sine of theta. So let's actually compute that for one of our problems. We kind of give away the answer here. That actually is going to give you the area of a parallelogram that's formed by those two things. So for example, if I had, here's my vector w, here's my vector v, let's say, that if we consider those to be two sides of a parallelogram, the other two sides of the parallelogram would just be here and here, right? So that would form a parallelogram. So this is how we can find the area of the parallelogram formed by those two vectors, v and w. You might be curious why. Even if you're not curious why, it's kind of important to know why. Well, notice that this formula involves sine of theta. So this is our theta. Theta is the angle between our vectors. If we think about what sine of theta means, we could think of it as if we drop down a vertical so that it's perpendicular with vector w. We know that sine of theta would be opposite. We don't have a name for that yet. The opposite side over the hypotenuse. Well, the hypotenuse is just the magnitude of vector v. So if I just base this off of the drawing I did, if I move vector v over, I'll have vector v sine theta equals opposite. So the magnitude of vector v times sine theta is equal to the length of the opposite side in my diagram here. So if I took that and replaced it in my formula, now this is the formula you're going to use. We're just sort of talking about how it's structured. We would end up with the magnitude of vector w multiplied by the length of the opposite side. Well, think about what that just gave us. The magnitude of vector w is the length of the base of this parallelogram. The opposite side is the height of the parallelogram. So if we think of the formula for area of a parallelogram as being base times height, this is just a manipulation of that. We have the length of vector w multiplied by what would be the height of our parallelogram, because that would be the opposite side of theta. So this is just a reconfiguration of the area formula for parallelogram, but using a vector product. So when we find the magnitude of the vector product, we are actually finding the area of the parallelogram that is formed. So let's go ahead and do that. Find the area of the parallelogram enclosed by the vectors. So I'm going to write out, first I'm going to need to know what the cross product between these vectors is. And then once I know what the cross product of the vectors are, I could find the magnitude of them. That would be one way of doing this. Another way of doing this would be to do the magnitude of each one and then multiply by sine theta. Well, how would we figure out what that was? We could do some work on that. But I think I'm just going to do the cross product and then find the magnitude of that. So let's find the cross product of these two. So I'm going to cover these up. I'll do -1 times 5 minus negative 4 times 2. Then for the y component, I start on the top right instead. So I'll do 1 times 2 minus 3 times 5. And for my z component, I'll have 3 times negative 4 minus 1 times negative 1. So I'm going to get negative 5 plus 8, so 3. 2 minus 15, so negative 13. Negative 12 plus 2, so, negative 12 plus 1, so negative 11. And then I can compute the magnitude of this to find the area. So basically, I'm just working out what this is. I'm not really using this right now. When would I use this? Well, it depends on the info they gave me. If they gave me the angle between the vectors, I could use this formula, or I could find the angle between the vectors too. That is possible. But I'm going to finish working it out this way. So 3 squared plus negative 13 squared plus negative 11 squared. And work that out. So I'll get radical, let's see, 9 plus 169 plus 121. So square root of 299, which is going to be approximately 17.3. They often would give you some sort of units. Let's pretend the units they gave us were in meters. So this would be meters squared. All right, another aspect I want to talk about, and this is going to go off the printed notes. I realized I wanted to talk a little bit about how the cross product, how this vector relates to the original vectors. So how does negative I plus 10j plus 7k relate to this vector and relate to this vector? I realized that had not gotten put in my notes. So you may want to grab a scratch piece of paper and draw that on a little bit. Okay, well, when you do the cross product of two vectors, so notice here we've got a vector going in direction A, we've got a vector going in direction B. I very well could have called these V and W, but this this picture already has it labeled A and B. If you do the cross product and then take the magnitude, we get the area of this parallelogram. That's what's labeled right here. The area of this parallelogram is A cross B, then find the magnitude. But what is the vector that you get when you do A cross B? Like, you get this vector. Why do I care about this vector? The reason I care about this vector is that this vector, V cross W, by the way, cross product, we have not proved that it's commutative. So that's why instead of writing V cross W and just leaving W cross V, I need it to be that order. Okay. So we have not proven if it's commutative yet. I don't believe we will. By the way, it's not. So V cross W, you need to make sure you do in the correct order. Anyways, when you do V cross W, you get a value, or you get a vector that is perpendicular to V, and that vector is also perpendicular to W. So what you get when you do the cross product is you get a new vector that is perpendicular to both vector V and vector W. If we think of where vector V and W are, or vector A and B, vector A and B live in 2 dimensions. They're just in 2 dimensions right now. If you think of them like, if you kind of consider 2 lines, 2 vectors would create a plane. But what you get when you do the cross product between them is you get a new vector that is perpendicular both to vector B and to vector A. It's perpendicular to both of those vectors. So if we think of A and B being on a flat surface like this, the cross product between those 2 vectors would be simply going straight up. That's why A cross B, that's why that vector is significant. A cross B, let's give him a new name. Let's give him C. C is perpendicular to vector A. C is also perpendicular to vector B. That's going to be important for the stuff that we're doing later on. Because now we're going to be able to figure out, like, let's say we have a plane and we want to know what vector is perpendicular to that plane. We're going to be able to compute that. That's going to be really important for a number of applications that we work through. By the way, there are some various terms that you may see besides the word perpendicular. They are synonyms for the word perpendicular. One of those is normal. So they may say, find the normal vector. They want the perpendicular vector to something. Another one would be orthogonal. Orthogonal is another word for perpendicular. It's just got different roots in different areas of math, but we use them all to represent perpendicular. So that is a significant result for us to realize. Let me make sure that there's one last concept that I wanted to briefly discuss. And that is like, okay, let me think of how I want to phrase this. When we're doing a cross product between two vectors, what we're kind of doing is we're seeing how much these two vectors are going in different directions. So when we calculate a vector product and then find the magnitude, that magnitude is a measurement of how much these are going in different directions from each other. To illustrate that, I'll just draw two examples. One, where vector v is closer to being perpendicular to vector w, and one where vector v is going much more closely in the same direction as vector w. And let's take a look at the definition that we talked about for this one, that the magnitude of vector w times the opposite side of the triangle we dropped down is what really the cross product is. So we have the magnitude of vector w in both cases, and we want to multiply that times the opposite if we drop down from vector v. So the opposite here is a much larger value than the opposite here. So for this one, we're going to have the magnitude of vector w times a small value. For this one, we're going to have the magnitude of vector w times a larger value. So we're going to end up with a smaller magnitude of our cross product for this, but a larger magnitude of our cross product for this. So the bigger the angle is between them, the larger your cross product magnitude is going to be. So what would produce the largest cross product magnitude? If v compared to w, how? If v was perpendicular to w, because that would be the greatest amount that this could be. If vector v was perpendicular to vector w, then if you drop down a right angle, you basically just get vector v. So in the case where they're perpendicular, the magnitude of the cross product is this highest value it can possibly be. This value here is as high as it can be. So that's why we kind of say, when you're finding the magnitude of the scalar product, when you're finding the magnitude, cross product is what I meant to say. When you're finding the magnitude of the cross product, what you're really finding is how much are these going in different directions. The bigger the magnitude of your cross product, the more different their directions are. So that's sort of just an intuitive thing that I wanted to talk about, more of a conceptual thing rather than a computational thing. But it is important for our understanding for when we move forward into some of our further lessons. Okay, that wraps it up for this video. Thanks for watching.